When the Lilium Jet appeared publicly in 2015, it looked like the future of aviation. No exposed propellers, no conventional tail, no giant helicopter rotors. Instead, it had a smooth manta ray-shaped body, dozens of electric ducted fans integrated into its wings and canards, and a cabin closer to a private jet than an air taxi. The promise was enormous: vertical takeoff, electric propulsion, regional travel, low noise, zero in-flight emissions. For years, Lilium looked like one of the strongest companies in the eVTOL race. Then, everything changed. Its main German subsidiaries entered insolvency in 2024. A rescue effort failed. Another insolvency filing followed in 2025. And by 2026, even the remaining prototypes reportedly struggled to find a buyer. So what happened? Was the technology impossible? Was the battery not ready? Or did Lilium simply try to solve too many difficult problems at once? The answer begins with the most distinctive part of the aircraft: its fans. The defining feature of the Lilium Jet was its propulsion system. Lilium called it ducted electric vectored thrust, or DEVET. Instead of using a few large open propellers like many other eVTOL aircraft, Lilium placed dozens of small electric ducted fans inside the wings and canards. The 2021 7-seat reference architecture used 36 ducted fans. Each fan had a shroud diameter of about 29.5 centimeters, or just under 1 foot. The duct itself was roughly 70 centimeters long. Later versions of the aircraft moved toward 30 propulsion units, but the 36-fan design is the version for which the most detailed public analysis exists. The concept was elegant. During vertical takeoff, the fans would point downward and lift the aircraft. Then, as the aircraft accelerated, the propulsion units would rotate toward the rear. The wings would begin carrying the aircraft, and the same propulsion system that lifted it vertically would now push it forward. No giant rotors, no exposed blades, no complicated helicopter-style transmission. The ducts could also offer safety advantages because the blades were enclosed. They could reduce tip losses. They could use stator vanes behind the rotor to recover some of the energy in the rotating airflow, and in theory, they could even help control noise. From a design perspective, it was beautiful, compact, integrated, futuristic. But aviation has a habit of punishing beautiful ideas when physics becomes involved. And the problem with Lilium was not whether the fans could produce thrust. They could. The real question was, how much power would it take? The Lilium Jet's reference maximum takeoff mass was about 3,175 kilograms. That is roughly 7,000 pounds. At that weight, gravity pulls the aircraft downward with a force of approximately 31,100 newtons. To hover, the propulsion system has to create at least the same amount of upward thrust. Divide that across 36 fans, and each fan needs to generate about 865 newtons. That is roughly equivalent to 88 kilograms of thrust per fan. And remember, that is only enough to hover. No climb, no maneuvering, no safety margin, just staying in the air. On paper, that was achievable. But this is where rotor size becomes critical. The total area covered by all 36 fan discs was only about 2.46 square meters. That produces what engineers call disc loading. Disc loading is simply the weight of the aircraft divided by the total rotor area moving air. For the Lilium reference architecture, the calculation produces roughly 1,290 kilograms per square meter. That number is enormous. By comparison, estimates cited in the original analysis for an aircraft like the Joby S-4 are generally around 46 to 60 kilograms per square meter, depending on assumptions. That difference tells us almost everything. Joby uses much larger propellers. Those propellers move a large mass of air relatively slowly. Lilium used a much smaller total fan area. That means its fans had to move a much smaller mass of air much faster. And moving air faster requires much more power. This is the fundamental physics problem. Imagine trying to lift a person using a giant industrial fan. Now imagine trying to lift the same person using a hairdryer. The small fan can theoretically create enough thrust. But to do it, the air has to come out incredibly fast. And that costs energy. Lilium did not have a thrust problem. It had a power problem. Using the aircraft weight and the 36-fan geometry, a simplified momentum theory calculation produces an ideal hover power requirement of around 1.2 megawatts. 1.2 million watts. For comparison, that is enough electrical power to run hundreds of homes. And that is only the ideal aerodynamic requirement. Real systems are not ideal. Motors generate heat. Inverters have losses. Batteries have resistance. Cables heat up. Fans are not perfectly efficient. Airflow around the aircraft interacts with the wings and body, and the aircraft still needs extra thrust for control, climb, and safety margins. Other published analyses have produced lower estimates under different assumptions. For example, around 500 kilowatts during a vertical climb. The exact number depends heavily on assumptions, but the larger point does not change. Vertical flight required enormous power, and this is where the contrast with aircraft like Joby becomes important. Large open rotors have more disk area. More disk area means lower induced velocity. Lower induced velocity means less power required to produce the same lift. Lilium deliberately chose small fans because they fit neatly inside the aircraft. They looked cleaner. They could be enclosed. They could potentially be quieter in some conditions. And they allowed a beautiful integrated design. But during hover, those advantages came with a major energy penalty. And once the aircraft needs megawatt-level power, the problem spreads into almost every other system. The battery, the wiring, the cooling, the motors, the inverters, the structure. Suddenly, the challenge is no longer just making an aircraft fly. It is making the entire electrical architecture survive the few minutes when the aircraft asks for almost everything it has. This may have been one of Lilium's hardest engineering problems. The aircraft needed a battery that could do two very different jobs. First, it needed high energy density. That means storing a lot of energy without becoming too heavy. High energy density gives an electric aircraft range. Without it, the aircraft simply cannot fly far. But Lilium also needed extremely high power density. That means delivering a huge amount of energy very quickly during takeoff and landing. These two requirements are not the same. A battery can be excellent at storing energy, but poor at delivering massive power. Or it can deliver enormous power, but store too little energy for useful range. Lilium needed both. And it needed both in an aviation certifiable battery pack. The company invested in silicon-dominant battery technology and partnered with a battery startup called Ion Blocks. Silicon is attractive because it can store significantly more lithium than conventional graphite. That creates the possibility of higher energy density. But silicon also creates serious engineering problems. It expands during charging. It can crack. It can damage the battery's internal structure. It creates challenges with cycle life, swelling, thermal management, and degradation. Those are serious problems in a phone. In an aircraft, they become certification problems. Because aircraft batteries cannot simply be impressive in a laboratory. They must be predictable, repeatable, safe, mass-producible, and reliable after hundreds or thousands of operating cycles. The power challenge becomes even more difficult during landing. At takeoff, The battery may be near full charge. At landing, it is not. Yet the aircraft still needs enough power to perform vertical flight safely. Ion Blocks published cell-level power figures of roughly 3.8 kilowatts per kilogram at 50% state of charge and about 3 kilowatts per kilogram at 30% state of charge. Those are impressive numbers. But Lilium did not only need good cells. It needed an entire aircraft battery system capable of delivering huge power repeatedly, safely, and within certification requirements. And that is where the difficulty multiplied. Here is the strange part. Once the Lilium Jet was flying forward on its wings, the aircraft potentially became very efficient. Earlier company material cited cruise power requirements below 200 horsepower, or about 150 kilowatts. That makes sense. Once the wings are generating lift, the fans no longer need to hold the entire aircraft against gravity. They only need to overcome aerodynamic drag. The aircraft's smooth shape helped. Lilium's technical assessment projected a lift-to-drag ratio of around 18.4 to 1 point. That is an impressive aerodynamic number. So in cruise, the Lilium Jet may have been elegant and efficient. But during hover, the aircraft could need more than a megawatt. Think about that difference. Approximately 150 kilowatts in cruise. Potentially more than 1 megawatt in hover. That is nearly an 8-to-1 difference. And this may be the most important thing to understand about the entire project. Lilium's biggest problem was not flying forward. It was getting off the ground. Because even if the aircraft only needs extreme power for a few minutes, every component involved must still be sized for that peak. The battery, the motors, the inverters, the bus bars, the cables, the switches, the contactors, the cooling system. All of it must survive the highest electrical and thermal loads. And all of that equipment has weight that must be carried during the entire flight. So a system designed for a few minutes of vertical flight becomes baggage for every minute of cruise. This is the hidden penalty of eVTOL. You carry the equipment required for hover even when you are no longer hovering. And for Lilium, that equipment had to be extremely powerful. Lilium also claimed another advantage: noise. Open propellers produce noticeable aerodynamic noise, especially at the blade tips. Ducted fans can offer advantages. The duct provides physical shielding. Acoustic treatment can potentially be added inside the structure. Blade tip losses can be reduced. And the rotor is hidden inside the shroud. But there is another side to the story. Small fans need to move air faster. Higher airflow velocity generally means higher rotational speed and higher frequency noise. So Lilium was dealing with a complicated acoustic trade-off. The ducts could potentially reduce some types of noise. But the very small fans that made the design compact also created high-speed airflow. Lilium argued that its duct design and acoustic engineering could keep the aircraft quiet enough for urban and regional operation. But the final full-scale production configuration never reached the stage where those claims could be completely demonstrated in real-world commercial operation. And this matters because noise is not a secondary issue for eVTOL aircraft. It is one of the biggest issues. A city may tolerate one aircraft. It may not tolerate hundreds flying over neighborhoods every hour. Urban aviation only works if communities accept it. That means the aircraft has to be not only safe and efficient, but quiet enough to live with. Lilium believed the ducted fan was part of the answer. But once again, the design was trying to achieve several difficult goals at the same time. Compact propulsion, high thrust, low noise, high efficiency, low weight, and vertical flight. Every one of those requirements pulls the design in a different direction. This leads to one of the most interesting questions in the entire story. What if Lilium had abandoned vertical takeoff? That sounds almost absurd. VTOL was one of the aircraft's biggest selling points. But removing VTOL may have removed the hardest problem. Consider a simplified conventional takeoff. Assume the same aircraft mass of 3,175 kilograms. Assume a conservative lift-to-drag ratio of 15. At around 50 meters per second, the aircraft might need roughly 104 kilowatts of useful aerodynamic power to overcome drag. If it climbs at 3 meters per second, another roughly 93 kilowatts would be required to gain altitude. After allowing for electrical and propulsion losses, the total wing-borne climb power might fall somewhere around 240 to 270 kilowatts. That is still a lot of power, but it is nowhere near the potential 1.2 megawatts required for stationary hover. In the simplified comparison from the original analysis, using a runway could reduce peak power demand by roughly 77%. That is enormous. Suddenly, the aircraft needs smaller electrical components, less extreme cooling, lower current, less battery stress, potentially lower weight, and easier thermal management. Of course, you lose vertical takeoff. Now you need a runway, and that removes one of the main reasons people were interested in Lilium. But it raises a fascinating possibility. Perhaps the best version of Lilium was never an eVTOL. Perhaps it should have been a very efficient electric regional aircraft, a premium short-range plane, a quiet electric business aircraft, or a short takeoff aircraft capable of operating from small regional airports. The technology might have been easier. The certification path might have been simpler, and the energy requirements would have been dramatically lower. Lilium bet heavily on vertical takeoff. In hindsight, that may have been the most expensive feature on the aircraft. The second major gamble was size. Lilium was not building a tiny one-seat machine. It was not building a lightweight recreational eVTOL. The reference architecture was designed for 7 seats. That created a heavier aircraft. And hover power does not increase gently as weight rises. For a fixed rotor area, ideal induced power increases with thrust to the power of 3 halves. In simple terms, a heavier aircraft becomes disproportionately harder to hold in the air. Add more passengers. You need more structure, more battery, more safety equipment, more power. Then you need stronger motors, larger inverters, more cooling, more battery. And now the aircraft becomes even heavier. This is the famous eVTOL weight spiral. Lilium was attempting to combine several ambitious things at once: a relatively large cabin, vertical takeoff, high speed, regional range, low noise, compact propulsion, and premium passenger comfort. Each feature was attractive individually. Together, they created one of the hardest aircraft design problems in modern aviation. This is why comparing Lilium only to helicopters or only to airplanes can be misleading. It was trying to be both. It wanted helicopter-like takeoff, airplane-like cruise efficiency, private jet-like cabin appeal, electric car-like simplicity, and urban air mobility-style accessibility. That is an extraordinary list of goals, and every extra goal adds engineering risk. Sometimes the problem with an aircraft is not that one idea is impossible, it is that too many difficult ideas have been stacked into one machine. Physics was only half of Lilium's battle. The other half was business. Aircraft companies burn money long before they make money. Designing an aircraft is expensive. Testing it is expensive. Certification is expensive. Building factories is expensive. Developing batteries is expensive. Developing motors is expensive. Training suppliers is expensive. And then you need enough money left to build aircraft before meaningful revenue begins. Lilium entered that process with one of the most ambitious architectures in the industry. That meant solving not only normal aircraft certification problems, but also unusual propulsion, battery, acoustic, structural, and flight control problems. Every year of delay costs money. Every redesign costs money. Every certification challenge costs money. Every prototype costs money. And unlike software, you cannot simply update an aircraft overnight. Hardware takes time. Aerospace takes even more time. Eventually, the financial runway became shorter than the engineering runway. In October 2024, Lilium's two main German subsidiaries entered insolvency proceedings. A rescue was attempted. That solution did not hold. Another insolvency filing followed in February 2025. And by April 2026, even the remaining prototypes reportedly failed to find a buyer and were being scrapped. That ending feels shocking when you look back at the beginning. A company once seen as one of the leaders of electric aviation ended with aircraft that nobody wanted to take home. But that does not automatically mean everything Lilium built was worthless. Far from it. The company accumulated knowledge in high-voltage electrical systems, electric motors, batteries, acoustics, flight control, aircraft structures, and distributed propulsion. The company disappeared. The engineering lessons did not. This may be the most important question. Was Lilium's idea fundamentally wrong? Or did it simply arrive before the technology was ready? One clue may come from newer aircraft concepts. Whisper Aero, for example, has explored concepts using arrays of electric ducted fans integrated into aircraft surfaces. That sounds familiar. But there is an important difference. Rather than forcing tiny fans to hold the entire aircraft in stationary hover, newer powered lift concepts can use the airflow from the fans to energize the wing. The wing then generates aerodynamic lift. Instead of asking the fans to do all the work, the aircraft makes the wing part of the lifting system. This could lead to very short takeoff distances or near eVTOL performance without paying the full energy penalty of pure hover. That may be where some of Lilium's ideas eventually survive. Not as a 7-seat aircraft hanging motionless on dozens of tiny fans, but as quiet electric regional aircraft, short takeoff designs, powered lift aircraft, distributed propulsion systems, or future hybrid concepts. Lilium may have been wrong about the configuration, but it may not have been wrong about the technology. Ducted electric propulsion still offers attractive features. Compact packaging, blade protection, potential acoustic treatment, integration into wings, precise electronic control, and distributed redundancy. The problem was asking that technology to perform the most energy-intensive task in aviation, stationary vertical flight, and asking it to do that on a relatively heavy passenger aircraft. That may have been one compromise too many. The Lilium Jet will probably be remembered as one of the most beautiful what-if stories of the electric aviation era. The aircraft looked extraordinary. Its aerodynamics were promising. Its cabin concept was attractive. Its propulsion system was innovative. And its vision was bold. But aviation does not reward ambition alone. The numbers have to work. The batteries have to work. The thermal system has to work. The propulsion has to work. The aircraft has to be certifiable. The company has to survive long enough to finish it. And the market has to be willing to pay for what eventually emerges. Lilium's ducted fans were not useless. Its batteries were not meaningless. Its engineers did not waste their time. But the aircraft may have been built around one requirement that made everything else harder: vertical takeoff. The small fans created high disk loading. High disk loading created extreme power demand. Extreme power created battery and cooling problems. Those systems added weight. More weight demanded more power, and the seven-seat aircraft pushed that cycle even further. Once flying forward, the Lilium Jet might have been elegant, efficient, fast, and surprisingly economical in energy. But the aircraft had to survive the most difficult few minutes of every flight before any of those benefits mattered. Takeoff, hover, landing. That was the paradox. Lilium built an aircraft that may have been excellent at cruising through the sky, but aviation required it to first escape the ground, and that may have been the challenge the company never fully solved. Still, Lilium's story should not be remembered only as a failure. Aviation advances because people attempt things that seem unreasonable. Some ideas work, some do not. Some disappear and return decades later in a different form. Lilium explored electric ducted propulsion, advanced batteries, integrated flight controls, quiet aviation, and distributed electric systems at a scale few companies had attempted before. Those lessons do not disappear because the company does. Perhaps the final legacy of Lilium will not be the Lilium Jet itself. Perhaps it will be an aircraft we have not seen yet. One that takes the best parts of the concept, removes the most difficult compromises, and finally makes the numbers work. Because sometimes the aircraft that changes aviation is not the first aircraft with the idea. It is the second one. The one that learns from everything the first one got wrong.